Every photo on your screen is just a grid of numbers. Before we touch any fancy math, I want you to really see that. A single operation, sliding a tiny window over that grid, is the seed of nearly all modern computer vision. Let's zoom into one small corner of that grid. Each square is a pixel, and its number is how bright it is. 0 is black, high numbers are white, and everything in between is gray. That's the entire raw material we get to work with. Now here's the question that convolution answers. How do we detect something meaningful in this sea of numbers? An edge, a texture, a corner. We can't look at one pixel alone. Meaning lives in how a pixel relates to its neighbors. So we build a tiny tool, a 3x3 grid of its own numbers. We call it a kernel, or a filter. Think of it as a little stamp that we're going to press down onto the image, one spot at a time. Here's the whole game in one move. We lay the kernel over the top left 3x3 block of the image, so each kernel number sits directly on top of an image pixel. 9 kernel values, 9 pixels beneath them paired up. Now we multiply each kernel number by the pixel directly under it. Top left times top left, middle times middle, and so on across all 9 pairs. This is the element-wise multiply, and it's the heart of everything. Then we add up all 9 of those products into a single number. Multiply, then sum. That one number is the kernel's answer to the question, how much does this patch of the image match what I'm looking for? That single number gets written into a brand new grid, the output. It goes in the position matching where the kernel was centered. We've turned a whole 9-pixel neighborhood into one meaningful value. Now we simply slide the kernel 1 pixel to the right and do the exact same thing. New 9 pixels underneath. Multiply each by the kernel, add them up, write the result. Same recipe, new location. We keep sliding right, one step at a time, filling in the output row. Watch how each new position only cares about a small local patch, yet together they scan the entire width of the image. This marching window pattern is what the word convolution really describes. When we hit the right edge, we drop down to the next row and start again from the left. Row by row, the kernel sweeps the whole image like reading a page. Nothing changes about the operation, only the position moves. Let's speed it up and watch the full sweep. Every landing spot produces exactly one output number from 9 inputs and 9 kernel weights. This is the entire convolution, a small, fixed rule applied everywhere. Notice something about the output grid. It's slightly smaller than the input. Because the kernel needs a full 3x3 neighborhood, it can't be centered on the very edge pixels. Those borders simply have no complete patch to sit on. In practice, we often pad the image with a ring of zeros around the outside so the output stays the same size as the input. It's a small bookkeeping trick. For now, just know the shrinkage is a natural consequence of needing neighbors. Let me pin down the math in plain terms because it's beautifully simple. Line up kernel weight with pixel, multiply every pair, add the results. A sum of products. That phrase is the whole formula, and we'll lean on it the rest of the way. Here's the magic we haven't touched yet. The operation never changes, but the kernel's 9 numbers decide what it detects. Change those weights, and the very same sliding sum starts finding completely different things. Let's build 3 famous kernels from scratch. Start with blur. Intuitively, blurring means each output pixel should be the average of its neighborhood, smoothing out sharp differences. So what weights give an average? Just put 1/9 in all 9 cells. Watch why that works. Multiply every pixel by 1/9 and sum. That's literally adding the 9 pixels and dividing by 9's the mean. Bright spots get pulled toward their neighbors, noise gets softened, and the image goes hazy. Show the before and after side by side. Fine detail dissolves, edges soften, the whole thing looks like it's behind frosted glass. And every bit of that came from 9 identical little weights and our same multiply and sum. Now the opposite goal, detecting edges. An edge is a place where brightness suddenly jumps, dark on one side, light on the other. So we want a kernel that outputs a big number when neighbors disagree and near 0 when they're all the same. Here's the clever construction. Make the center weight large and positive, and the surrounding weights negative, arranged so they all sum to 0. When the patch is flat, the pluses and minuses cancel, output 0. When there's a jump, they don't cancel. Let's test it on a flat gray patch, where every pixel is the same. The positive center and negative surround exactly cancel, and the output is 0. No edge here, so the kernel correctly stays silent. Now slide it across a real boundary. Suddenly the neighbors no longer cancel, and the sum leaps to a large value. The output grid lights up exactly along the edges of the image, and stays dark everywhere flat. This is worth savoring. We didn't program in the concept of an edge. We just chose 9 numbers that cancel on flat regions and fire on jumps, and the sliding sum found every boundary automatically. The intelligence lives entirely in the weights. One more classic, sharpening. The idea is to take the original image and add back the edges we just found, making boundaries crisper. We can fold that whole idea into a single kernel. The sharpened kernel keeps a boosted positive center with mild negative neighbors, but this time the weights sum to 1 instead of 0. That means flat regions pass through unchanged while edges get exaggerated. Same machinery, one tweak to the balance. Run it, and details snap into focus. Edges gain contrast while smooth areas stay put. Blur, edges, sharpen. 3 utterly different visual effects, 1 identical operation. The only thing that changed was 9 numbers. Let's line all 3 up together with their kernels. This is the key insight to carry forward. The sliding sum of products is a general-purpose machine, and the kernel is its program. Now, what if we didn't choose the numbers ourselves? That's the leap into deep learning. Instead of hand-picking weights, we let the network start with random numbers in its kernels and adjust them through training until they detect whatever helps it succeed. The operation is frozen, the weights become learnable. A convolutional neural network, a CNN, is built from exactly the operation you now understand, repeated at scale. Its first layer slides many different learned kernels over the image, not just one. Each kernel produces its own output grid. Each of those output grids is called a feature map. It's a picture of where in the image that particular kernel fired. One map might light up on vertical edges, another on horizontal ones, another on little blobs of texture. So after one layer, instead of a single grayscale image, we have a whole stack of feature maps, say a few dozen of them. Think of it as a deeper image, where each layer of depth answers a different simple question about the picture. Now comes the beautiful part. What if we run convolution again, but this time over the stack of feature maps instead of the raw pixels? The kernel now sees not brightness but the outputs of the first layer's detectors. A second layer kernel spans the full depth of that stack, so it combines several first layer features at once. It might learn fire when a horizontal edge sits above a vertical edge. In other words, it detects a corner, a combination of simpler parts. This is the whole idea of hierarchy. Layer 1 finds edges. Layer 2 combines edges into corners and curves. Layer 3 combines those into textures and simple shapes. Each layer builds on the vocabulary of the one below it. Between these convolution layers, networks usually shrink the maps down, pooling neighborhoods into single values. This zooms out, so each later kernel effectively sees a larger region of the original image while still only looking at a small local patch of its input. Stack enough of these layers, and the receptive field grows enormously. A single number deep in the network now depends on a huge swath of the original image, assembled through many rounds of the same little multiply and sum. Depth turns local rules into global understanding. By the deepest layers, the feature maps respond to genuinely high-level concepts: an eye, a wheel, a paw, the loop of a handwritten letter. No one programmed these detectors. They emerged because training tuned millions of kernel weights toward whatever made the predictions correct. And every single one of those detectors, from the first edge kernel to the final object part kernel, is doing the exact operation from the start of this video. Overlap the window, multiply each weight by each value, add them up, move on, nothing more. Let's zoom all the way out and see the full pipeline in one shot. Raw pixels enter on the left. Convolution and pooling layers transform them into ever richer feature maps, and by the end the network can name what it sees. Think back to where we began. A lifeless grid of brightness numbers and one tiny window sliding across it. The entire tower of modern vision is that window, stacked and repeated, with its weights learned instead of guessed. The lesson is that enormous complexity can grow from one simple repeatable rule, sum of products, applied locally, everywhere, over and over. Understand that single step deeply, and you understand the engine inside every image the machine has ever recognized. So next time you hear that a model saw a cat, you'll know what really happened. A grid of numbers met a cascade of sliding windows, each multiplying and adding, edges becoming shapes, becoming meaning. That's convolution, and now it's yours. If this made it click, subscribe for more visual math.